So, hello to everyone who's watching on YouTube. Uh, I'll get started in 5 to 10 minutes. I'm just waiting for a few students to join the session in person. So, we'll get started in like 10 minutes. Okay, hello everyone. I'm facing some technical issues with my laptop. So as soon as it gets sorted, we'll get started with discussing the questions. Like, since no one has joined the session in person, I guess I'll just start with addressing the YouTube audience as soon as I fix the technical issues with my laptop. So sorry for the delay. So I'll be muting myself till then. Hopefully it gets resolved in like 5-10 minutes. Okay, so sorry for the delay, guys. There were some technical issues with the laptop. Nevertheless, I guess we can get started with the session. So first of all, just to reintroduce myself to the YouTube audience. So hello everyone, I'm Lakshya Saggi, the problem solving TA for the NPTEL Games and Information course for the Monday 6 to 8 p.m. sessions. But this time around, like because I had some scheduling issues, we are having this session from like 3 to 5 p.m. But from next week onwards, the session will still occur from like on Monday 6 to 8 p.m. only. It was only for this week. So yeah, this is I guess our eighth session, and in this session we'll be discussing problems related to like equilibriums in dynamic games, single act games, and like different sorts of equilibriums which are discussed in this week's lectures. So I guess I'll just get started with so I'll just share my screen and we can get started with discussing the problems. So let me just share my screen. Okay then. Uh, so since in this week like there were a lot of different types of equilibriums or different kinds of like theory concepts covered, so I just thought it's maybe a good idea to just give a brief overview or brief summary of whatever the main things which were discussed in this week's lectures, so that one can have kind of like quick revision notes, that kind of a thing. So first, in this week, there was discussion around equilibrium in dynamic games, and like this has been covered in previous weeks also, but just for completeness sake, I mentioned it here also. So dynamic games, uh, uh, in like equilibriums or dynamic games, this was discussed last week, in previous weeks also, that a dynamic game inherits equilibrium from informationally inferior games. So if there is an equilibrium in an informationally inferior game, then in the actual game also be a Nash equilibrium. So whenever we are talking about just equilibrium, we mean Nash equilibrium. That's kind of obvious. And to find all possible Nash equilibria, we just have one thing, which is like normal form. So we have to convert the game into its not. We have to convert an extensive form game into its normal form if we want to obtain all possible Nash equilibria. Okay. And yeah. And another property is if J is a game with perfect information, so is a game with perfect information, then an equilibrium. So then one of the possible Nash equilibrium can be found by backward induction. So backward induction is trying to at every stage of the game trying to find out the best possible move for a certain player so that the player's profit is maximized or minimized, that kind of thing. So if G is a game with a perfect information, then if we find out the set of strategies which using back the set of strategies using backward induction, then that strategy profile will also correspond to one of the Nash equilibrium. So if every player tries to take the best step at every stage of the game, then that will correspond to one of the Nash equilibrium. But note that this technique doesn't give us all the possible Nash equilibrium, because we learned about like threat equilibriums also, right? And threat equilibriums are essentially where a player plays irrationally to harm himself as well as another person. So that kind of a thing. And then there was discussion around nested extensive form game. So what's a nested extensive form game? So an extensive form game is said to be nested if each player has access to the information acquired by all of its predecessors. So essentially, what this means is in the extensive form games tree, for any node, the information which that node has should be at least as much as the information that its previous node has, that its ancestral node has. For example, in this kind of a diagram, if we look at any of these nodes of P3, then this node of P3 knows that P2 has played, but it does not know what P2 has actually played, because these two nodes are in the same information set. But this set of nodes, but they know that P1 has played the right side. So this set of nodes of P3 know that P1 has played the right move and P2 has played something, but they don't know what P2 has actually played, right? And you can see in the ancestor also, these nodes ancestor is this right node of P2. This ancestral node just knows that P1 has played something. It doesn't even know what P1 has played because these information sets, these are the same information set. So essentially, these nodes of P3 have more information than, even more information than the information which these nodes have. So we can kind of say that this is an example of a nested extensive form game that this node, like uh, for all players, like we can check this for all players also, like for all players, this kind of thing should hold that all the ancestors should have uh, lesser information or like equal information to the actual node. And like high level, like if you want to say, okay, like just give me a crisp idea of what this means, like do I have to check for like every node, like what kind of information it has, what kind of information it does not have. So on a high level, what this nested extensive form game just means is that if at any node like there's an information split, so for a certain player, suppose two nodes are in the player's head but they are in different information sets, then in all of the like uh and then in all and then whole of these subtrees, like suppose these two nodes of P2 were in two different information sets, then no two nodes of these two subtrees of P2 should be in the same information set. So what this essentially means is that if there is a break in an information set at like uh, upper level, then there shouldn't be, then those two nodes should not then there should not be any association of information sets between those two subtrees. Like what I kind of mean is that if these two nodes were in different information sets, then their subtrees should not have any two nodes which belong to the same information set. So if there was like division, let's say like these two nodes of P2 were in different information sets, then none of these nodes and none of these two nodes should be in the same information set. Like one from here and one from here should not be in the same information set. So this is a high level uh, idea of what a nested extensive form game essentially means. It just means that division of information at a higher level like continues at a carries forward at a lower level also. So if there is a division of information at some upper node, then that same division will continue to be there in like lower nodes also. So yeah, I hope it makes sense. And then we talked about what are ladder nested extensive form games. So ladder nested extensive form game is just an extensive form game is said to be ladder nested if it's nested. So first of all, the game should be nested because it says a nested extensive form. And there should be another property for it to be called ladder nested. That the only difference between the information of a player PI and its immediate predecessor PI minus one is the actions of PI minus one, and only at nodes corresponding to branches emanating from pi minus one singleton information sets. So note that we are just right now talking in the domain of, let's say, single act games only. We are not talking about multi-act games, and we're defining all of these settings for just single act games. Though these definitions can carry over to multi-act games also, but they just stick to single act games. So what this kind of means is that this has already been covered, but again, just mentioning that a game is ladder nested if it is nested, and there should be an additional property that for a player pi and its immediate parent pi minus one, uh, suppose and there's a player pi and its immediate parent is pi minus one, then the difference between information of player pi and pi minus one should just be the actions of pi minus one. So PI so note that the game is nested, right? So PI will have more information or equal information to its parent PI minus one. So what's a ladder nested game then? Then it says that if there is a difference between the information of PI and PI minus one, then the difference should only be in the actions of PI minus one. So there should not be any more difference than the actions of PI minus one, and it should be only at nodes corresponding to branches emanating from pi minus one singleton information sets. So the difference should be between actions of pi minus 1, and it should only be at the actions which correspond to like singleton information set nodes of pi minus 1. Uh, so I hope this makes sense. And from this diagram, if we see what this means is like we can see that this game is kind of ladder nested. And why is the case? Why is this the case? So first of all, let us convince ourselves that it is nested. So on a high level, we can see that there is a division of information at player 2, and note that this division of information carries forward to player 3 also. Like no two nodes of these subtrees are in the same information set. So this is in one and these are in others. So there is no association between these two subtrees. So we can say that this is a nested game. And why is this also a ladder nested game? So let's just consider the player P3. So P3, and let's say this, so let's say this is the information set of P3 and this is the information set of P2. Like its immediate parent is this node. Then we can see that actually these two nodes have the same information because P3 just knows that P2 has played, but P3 does not know what P2 has played. So actually these two nodes have kind of the same information that P1 has played in. So there is no difference here. But if there is a difference, then it should only be at the singleton nodes and it should only be about the actions. So right now there is no difference. So here we are fine. Till now it's a ladder nested game. And let's just suppose we consider this information set of P3. Then we can see that again, this information set of P3 knows that P2 has played this third node and knows that P1 has played R. Whereas P2 just knows that P1 has played R. So there is some information difference between this node of P3 and this node of P2. But note that the only difference is this node knows that P2 has played something. So only difference between information sets of like this node and this node is the action of the player P2. And this action emanates from singleton information set of P2. So till now also it's ladder nested. So note that uh, if there is a difference in information, then the difference should only correspond to action of P2, which we see here is it is the case, and that action should be taken at a singleton information set of P2. So note that this is a singleton information set because this is just a single node. So we can definitely say that till now also game is ladder nested. And here for P3, again, for this set information set of P3, we know that P1 has played R, and it also knows that P2 has not played this branch. So it knows that P1 has played R and P2 has not played this branch, whereas P2 just knows that P1 has played R. So the only difference between information of this information set and this information set is the action of player P2, that P2 has not played this. And this action emanates from like a singleton information set of P2 only. So again, also till here also, it's a ladder nested game. So we can say that this whole game is of ladder nested form. Right? And then like why are we discussing about these ladder nested extensive form games? It's just that if one wants to find out a Nash equilibrium in a if one wants to find out just one Nash equilibrium in a ladder nested single act game. So note that if the game was a perfect information, if the game was a perfect information, suppose all the information sets were singleton sets, then we know that an equilibrium can be found by backward induction. But now, suppose the game is not a game of perfect information. There are some information sets which are non-singleton. Then that's the case where we are talking about these nested games and ladder nested games, and we are talking about information sets here because now in these kinds of games where the game is not a perfect information, direct backward induction will not necessarily lead to an equilibrium because many players don't even know what a previous player has played or what the previous player is going to play. So that's why in these kinds of settings, finding equilibrium is not trivial, and that's why we define these kinds of ladder nested games and something. And then actually, if we define these ladder nested extensive form games, then actually, like this is a relaxation of general extensive form games, right?
like it's not necessary that every extensive form game will be in ladder nested form, but if the game is in ladder nested form, then also we can say that it's not too difficult to find a Nash equilibrium. So if you want to find any one Nash equilibrium for these ladder nested single eye games, then this was the algorithm discussed, uh, which just on a high level says that just consider like it's very similar to the uh, backwards induction argument, but just says that like partition the game into multiple simultaneous games. So partition the dynamic game into multiple simultaneous games and find out equilibriums for all those games, and together you can find out the and using those you can find out the actual equilibrium for the ladder nested game. So what this means is just for if each information set of the last acting player, so we are kind of doing a backward induction here also, but a smarter backward induction. So first we see all the nodes at the last which have the same information. So all the nodes which have the same if first we find out the set of nodes which have the same information. So for those set of nodes, the game is actually a simultaneous game because everyone knows the same information. Uh, the difference between dynamic and simultaneous games is this itself, right? That in dynamic games, the information gets updated one by one, where in simultaneous games, everyone just knows at the start what the information is. So just consider the game fair, just consider a set of players at the end which have the same information and players and find out Nash equilibrium from the simultaneous game for those games. And sorry for that, guys. And then you can and then you can replace the whole game which you had uh, by this static game, the simultaneous game and its equilibrium. And then basically like you do in the game with perfect information that you replace a branch by uh, the actual equilibrium cause. So this is what you'll be going to do here also, that uh, just find out a branch and like just consider those set of nodes which have the same information, and then for those set of nodes find out like simultaneous Nash equilibriums, play a simultaneous game and find out Nash equilibriums, and then replace the whole set of nodes which were there which formed this game by just one node which corresponds to the Nash equilibrium node. And we just keep repeating this till we go to the root. And this is uh, like an equilibrium. So this is just so in this game, so you can see that it's not like uh, very difficult to see why is this true. It's just that we are doing so first we defined equilibrium for perfect information game, and now we want to define like some kind of games where even if the game is not a perfect information, we are still able to find an equilibrium, an Nash equilibrium. So this kind of idea just extends the perfect information backward induction idea to the ladder nested games. For example, here, let's see in this example, like this is a ladder nested game. So it can be seen here that this P3 and this P2 actually have the same information, like this node of P3 and this node of P2. This information set and this information set have the same information that P1 has played in. So actually, what one can consider is uh, in this part of the game, in this tree of the game, P2 and P3 are actually playing a simultaneous game. And if they are playing a simultaneous game, you can just find out a Nash equilibrium for this simultaneous game and replace this whole subtree by just the Nash equilibrium which you obtain. So you remove all of the subtree and just replace it by the uh, Nash equilibrium which you can obtain. Similarly, here uh, one can actually see that here P3 has more information than P2. Here also it has more information than P2. So you just replace these nodes by the Nash equilibriums for the like so like you can't say that P2 and P3 here are playing a simultaneous game. So here they are not playing a simultaneous game. Here you just see what kind of actions would P3 take in these kinds of scenarios, and here what kind of actions would P3 take, and then just replace these nodes by the costs which you'll opt. So basically, you just remove this subtree and these whole subtrees of P3 by just the equilibrium cost which you obtain. Or if just P3 is playing, and then you can see like a set some of the branches have been removed, and now the action of P2 determines to which equilibrium um, will you be going, and then like you can recurse on P2 also, like what step is P2 going to take. Similarly, like here also you can recurse and till you reach the root, and you can show that this will form an Nash equilibrium. Okay, then. And then so this was the discussion till single act games, and now suppose we are talking about multi-act games. So then there was discussion that multi-act games in general are very difficult to analyze. So we have some kind of a relaxation for multi-act games, which we call stage-wise multi-act games and feedback forms of those games. So multi-act games are where one player can play multiple times, but they are very hard to analyze usually. And we have a relaxation, like it does not cover every multi-act game, but we say that usually stage-wise multi-act games are much more easier to analyze. Even though every multi-act game may not be, uh, we may not be able to convert to a stage-wise multi-act game, but the games which are in stage-wise multi-act form are indeed easier to analyze. So we look at those games. And so, what's a stage-wise multi-act game? The game tree is divided into stages, and what is meant by a stage? A stage is uh, a stage is when each player plays once in a stage. Like we define the stage of the game as a point where a point like, so we have a notion of kind of a time, let's say, in a stage-wise multi-act game. So we say that till time one, every player has played once, and then till time two, every player has played twice, till time three, every player has played thrice, and so on. So this is, you can consider the notion of stages as a notion of time. So at t equal to 1, every player has played once, t equal to 2, every player has played twice, and so on. But note that uh, so, and also like there's another relaxation in stage-wise multi-act games that at time equal to 2, the information obtained at the end of time equal to 1 should not be lost. So whatever is done after each player has played once should not be lost when the players start moving the second time. So no information set contain nodes from more than one stage. Okay, like I think yeah. So no information set contain node from one stage, because this is because of the notion of time, that at time equal to like you can't have information sets corresponding to two different times, right? Because no one knows the future and something like that. And then like what I was discussing was this feedback form that the first acting player in each stage has a singleton information set. So why is this that the first acting player in each stage has a single information set? This is because like every player should know what transpired at the end of the previous stage. Like at the start of stage two, you should know like what happened at the end of stage one. And if you have like, let's say the P3, like these blue and red node were actually in the same information set, then actually P3 does not know what happened at the end of stage one clearly, because P3 is confused between this branch and this branch. So in stage one multi-act games, like in their feedback form, we know like what happened at the end of time equal to 1 before starting moving in time equal to 2. And similarly for future times also. And like note that this should also not be violated at at movements of other players. Like suppose P4 moves later in stage 2, then this information should also not be lost for P4. Like P4 should also know what happened at previous stage. And that's why like these two information sets, these two nodes should not be in the same information set, because if these two are in the same information set, then this means that P4 has lost some information of what happened at the end of stage one, because like these two branches lead to these two different nodes, but they are in the same information set. This is just the fourth condition, that information sets of other players are such that none of them includes nodes corresponding to branches emanating from two or more different information sets of the first acting player of the stage. So the first acting player of the stage, and uh, none of the players should include branches emanating from these two different information sets. So yeah. So these are the four conditions, and if these four conditions are satisfied, then you say that the game is a stage-wise multi-act game in its feedback in a feedback form. And why is this useful? So in these kinds of games, it turns out that it's easier to analyze and find out a Nash equilibria. And one and like one possible Nash equilibria is the feedback Nash equilibria, and which is just generalization of the Nash equilibria of the single act games. So what this feedback Nash equilibrium means is so first of all, if the single act games at each stage is ladder nested, then the actual multi act game is said to be like ladder nested feedback form. Is said to be in ladder nested feedback form. And what's a feedback Nash equilibria? So a feedback Nash equilibria essentially says that on a high level, what this feedback Nash equilibria says is that if the game is in let's say multi act feedback form, then at every stage you can consider a Nash equilibrium on its own. So what you can do is, if you want to find out the Nash equilibrium of this whole multi-stage game, which has k stages, then what you can do is, uh, you can consider first the stage k, and so it's kind of a backward induction like argument. Just consider the stage k, and in stage k, there are multiple branches, and so for every branch you find out the Nash equilibria. Just considering this stage, ignoring what has happened in the previous stages, just considering these branches, find out Nash equilibria. And if these games are in ladder nested form, then it's easy to find Nash equilibria in these games. And then what you do is, you just replace all of these branches with just the Nash equilibria values, and then just consider the stage k minus 1, and then find out the Nash equilibria. And then so basically it's kind of a more advanced backward induction argument, that you first apply backward induction on stage k, then k minus 1, then k minus 2, and so on. And while applying a stage k, you can forget about the stages 1 to k minus 1. And this is only true if the game is and this will lead to a Nash equilibria. One needs to prove that this will lead to a Nash equilibria, but it's easy to show, and just bear with me, and just assume that this kind of procedure will lead to one possible Nash equilibria if the game is in feedback form, if the multi-act game is in feedback form, if all of these conditions are satisfied. It's a stage-wise multi-act game in its feedback form. And just a mathematical way of writing this is, so at stage k, like if you consider any, so these gammas are just the actions at different stages. So this gamma 1 is at action at stage 1, stage 2 till gamma k minus 1. So for any possible actions till first k minus 1 stages, so any possible actions will lead to any possible start state for the stage k. So what this says is that for the kth stage, uh, for any set of possible actions till previous stages, one should obtain a Nash equilibrium for the kth stage. If the set of actions till first k minus 1 stages remains the same, then it should be a Nash equilibria for the kth stage. And similarly, for k minus 1th stage, again, this is kind of a definition for k minus 1, that if the actions till k minus 2th stages remain the same, then the action till k minus 1 should form a Nash equilibria or something like that. So note that this is what is called a feedback Nash equilibria. It's not obviously very clear directly from these statements, okay, this is, if someone defines these kinds of conditions, why is it an actual Nash equilibria? It's not very clear, because in actual Nash equilibria, uh, these gammas can also vary, right? It's not that And this is because like this player I is acting in these previous stages also. Like this ith player is not just acting in the kth stage, it's acting in previous stages also. So in an actual Nash equilibrium, what's going to happen is it should not be just gamma I of k, it should be gamma I of k, gamma I of k minus 1, gamma I of k minus 2, and so on. But what one can show is like if you just consider it stage wise also, like if you find out in stages also, and let's say the game is in this kind of a form, stage wise multi-act form in feedback form, then this will lead to a actual Nash equilibrium also. I hope this is clear. I'll just mute myself for a minute, guys. I need to drink some water. Okay. So I hope this kind of makes sense that like this condition is not actually an Nash equilibrium condition, but what we can show is if all of these conditions are satisfied, then you will obtain one possible Nash equilibrium. Like it does not give us all possible Nash equilibria, but one possible Nash equilibrium will be obtained, and we can say that this equilibrium is called a feedback Nash equilibrium. Like if the game is in like stage wise multi-act feedback form, then like you can obtain one possible Nash equilibrium using this. So note that in this week all of the lectures like were focused on like kind of finding out the Nash equilibria. Like if there exists even one equilibria, let's say we want to find, like there can be multiple Nash equilibria, but finding all of them is like kind of a hard problem, but we still want to find at least one possible equilibria. And all of these games and formulations are just so that we can find Nash equilibria in different kinds of settings, in single act games, in multi-act games, and stuff like that. So like let's just keep the higher objective of the lectures in mind, that we are interested in finding out the Nash equilibria. And then what's a feedback Nash equilibrium of delayed commitment type? So what's a delayed commitment? So delayed commitment type is nothing but, okay, like in a game with perfect information, we said that there exists some threat equilibriums, right? Uh, and we said that like one possible like best like using the backward induction argument, one can say that if a player takes the best possible action at every step, then one obtains a Nash equilibrium. So similar kind of thing can be said for like games where every player takes the best possible action corresponding to the information that player has at every step. So in a general game which has imperfect information, we need to find out we can find out one possible equilibrium using this kind of algorithm, right? And this kind of algorithm essentially says that every player is playing its best corresponding to the information that player currently has. In a game with perfect information, every player has all the information. But in a general game, let's say the game is in ladder nested form, every player does not have all the information. So the player plays according to the best possible moves according to the information it has. So it's partially rational, you can say, or something like that. So so for this kind of, if you apply this kind of algorithm, it's usually called that the equilibrium obtained is of delayed commitment type. And why are we saying this as delayed commitment? Because like in a threat equilibria, usually like what happens in a game with perfect information, threat equilibria occurs when someone commits to doing some harm to the other person or something like that. So when a person plays irrationally, but here the person is not, no one is playing like irrationally, but it's playing like rationally according to the information given available to them. That's why like it's just a nomenclature that the game is called, that the equilibrium obtained is called of delayed commitment type. So what's a feedback Nash equilibrium of delayed commitment? So delayed commitment type is a like for it's defined for single act games. Like you can like what I said was like the equilibrium obtained here is what you call a Nash equilibrium of delayed commitment type. Like using this algorithm, the equilibrium you obtain is called the equilibrium with delayed commitment type. And then what's feedback Nash equilibrium of delayed commitment type? It just says that a feedback Nash equilibrium is set to be delayed commitment type if the appropriate restriction at each state is the delayed commitment type equilibrium for the corresponding single act game. And what this means is that so note that we are in this feedback Nash equilibrium. What we are saying is let us ignore the first k minus one stages, and for each of the uh, sub games of the kth stage, just find out Nash equilibriums and keep on doing this till you obtain stage one, till you go to the root. So note that in stage k, if one is interested in just finding a Nash equilibrium for the stage k, then it's a single act game, and in that game there can exist threat equilibria also, right? So there can be different kinds of Nash equilibria. Like it can be a threat equilibria, it can be like a delayed commitment type equilibria or something. And you can replace all of these by threat equilibria also and obtain one uh, Nash equilibrium here. But if you do like this algorithm, the delayed commit, if you try to obtain the Nash equilibrium of delayed commitment type for every stage, and you keep on doing this algorithm only for every stage, that you find out Nash equilibria of delayed commitment types at every stage, then the Nash equilibria which you obtain at the end is called the feedback Nash equilibria of delayed commitment type. I hope this kind of makes sense. That if you are finding out a so delayed commitment type Nash equilibrium is defined for single act games. And now if you're doing this delayed commitment for like every stage of the multi-act game, then the final equilibrium which you obtain is called feedback Nash equilibrium of delayed commitment. Like feedback Nash, like this delayed commitment type is more of a concept for single act games, and feedback Nash equilibrium is more of a concept for multi-act games. So in a multi-act game, if you apply like for all the single act games, the delayed Nash equilibrium, then the final equilibrium which you obtain for the multi-act game is called the feedback Nash equilibrium of delayed commitment type. Yeah, a lot of terminology, but just note that all of it makes quite an intuitive sense if you are able to grasp the high level idea. Like you don't need to like go into these proper definitions and everything. You can go like, but if you understand the high level idea, you can write these definitions yourself also. So yeah. Okay then. Then like I thought like this week it's more important to cover all of these theory concepts because yeah, there were a lot of equilibriums and those kinds of things discussed, and it might get a bit confusing and overwhelming for a student. Like, what is this? What is that? And why is it there? Why is this not there? So I just thought maybe we should discuss a high level overview of what was discussed and why it was discussed. So essentially, we have discussed the what and why is because like we are interested in finding out Nash equilibriums for different kinds of games. Yeah. Okay then. Then I guess we can move on to like questions again. Like questions are based on like these kinds of theories only, which we discussed, and I don't think you'll find the questions to be too difficult. But nonetheless, let's get started with them. So the first question is again some warm. Should we have initially some warm up questions like which were discussed directly in the lectures or something? So the first question says that a threat equilibrium can exist. Okay. So the first question is a threat equilibrium can exist in a zero sum game. Is this true or false? So note that like this problem was discussed in the lectures also, but I'll just discuss it nonetheless. That what's a threat equilibrium? Usually, in a threat equilibrium, one player commits to taking some action irrationally, and the logic behind that action is saying that okay, I'm going to harm myself to harm you more. So let's consider just a two-player game. And what does a threat equilibrium mean there? Player one says that I'm going to take a hit for myself so that you are hit even more. And this kind of commitment scares the other player, and this gives us some kind of a Nash equilibrium. Uh, like I'm just talking on a very intuitive level, not a very mathematical level. So in a threat equilibrium, what one player issues a commitment which is a harm to itself also, but it also harms the other player. That is the rationale behind threat equilibriums. But note that if the game is a zero sum game, then one person's loss is another person's profit. So I can't. So player one cannot give an argument that okay, I'll harm myself to harm you even more. Because if I harm myself, then the other person will be gaining because it's a zero sum game. So the concept of threat equilibrium only exists for like non-zero sum games. For a zero sum game, the concept of threat equilibrium does not make sense because you cannot like take a hit for yourself so that the other person is hit even more. Like if you are hit, then the other person is actually gaining something in a zero sum game. So I hope this makes sense. So this kind of treatment is. And why is this false? Maybe I should have said. Uh, so in a more mathematical sense, if I just want to say like, okay, maybe I'll just write this down and then discuss in a threat equilibrium. One player a player issues a threat which harms the player itself but harms the other player. Okay, maybe a threat equilibrium exists because a player issues a threat which harms the player itself but harms the other player even more. However, if the game is a zero sum game, maybe I should write that this is a very intuitive argument. Like this same argument was discussed in the lectures also intuitively, but yeah, let's just write this down explicitly again. However, if the game is a zero sum game, then the player um then if a player harms itself, the other player will always be gaining something. And hence, threats don't work in a zero sum game. Okay, yeah. So this is the high level rationale behind like threats only work if one player harms itself, and so that the other player is harmed even more. And the other player they get scared and like does not like play rationally or something like that. But in a zero sum game, this does not occur. And mathematically, how can you formulate the same argument? So in a zero sum game, so suppose you convert the given extensive form game into a normal form, then we had already discussed, like this has been discussed previously in the lectures, that in all the Nash equilibria of in all the Nash equilibria of a game, in of a zero sum game, the saddle like basically all the saddle points have the same values in a zero sum game. In a zero sum game, all the saddle points have the same value, and if this is true, then basically every Nash equilibria has every player gains the same amount in every Nash equilibria in a zero sum game, and this essentially means that if you obtain one Nash equilibria, so we know that one possible Nash equilibria can always be obtained by using backwards induction or the arguments of the kind which we discussed previously, then all the Nash equilibria will correspond to uh, all the Nash equilibria will have the same values as the one which you obtain using the backward induction or when the player actually plays rationally. And this essentially means that if a threat equilibrium existed, then threat equilibrium was actually equivalent to a rational equilibrium only, and like this kind of does not make sense, right? So yeah, this is a more mathematical, like not totally mathematical argument, but yeah, a more mathematical argument would be saying that all the saddle points in a zero sum game have the same value. So how can a threat equilibrium and but then if the threat equilibrium exists and let's say a rational equilibrium exists, then how can the threat equilibrium and the rational equilibrium have the same values or something like that? Yeah. Okay, then. So let's move on to the next question. So this is the common data for questions 2 and 3. So let's consider the following game. So this is a game between three players, P1, P2, and P3. It's single act games and all the players are playing only once. And so we have to pick the correct options for the game one. So in the RHS game, so let's say we do it option by option. Okay, I think we need to move everything to next page. Yeah. So let's do it option by option. So in the RHS game, P3 knows that P1 has played R1. So note that these are so these highlighted things are the information sets of the player 3. These are player 2's single information sets, and this is player 1. So in the RHS game, so RHS game is this right side, like basically when P1 plays R1. So this is the RHS game, the right side of the tree. So in the RHS game, P3 knows that P1 has played R1. So let's see what does P3 know in this game. So in this game, the information set of P3 is this, and this information set actually can distinguish between whether P1 has played R1 or L1. So this information set is only achieved if P1 plays R1. So this statement is actually true. Like in this RHS game, P3 actually knows that P1 has played R1. So so I don't think I need to write the explanation for this. Like this is evident from the diagram only. Yeah. Now let's move on to option B. So option B is in the RHS game. So again, we are talking about RHS game. P3 knows if L2 was played by P2 or if R2 was played by P2. So what the option B is saying is that P3 knows if L2 was played by P2 or R2 was played by P2. So let's see, like in the RHS game, like these two, so P2 plays L2 or R2, but note that these two nodes are in the same information set. So actually P3 does not know whether P2 has played L2 or R2. So this statement is incorrect. So this statement is actually incorrect. Like I don't think I need to write down explanations for this because it's clear from the diagrams only. Like L2 and R2, the the nodes corresponding to actions L2 and R2 are in the same information set as the nodes of P3 corresponding to actions L2 and R2 are in the same information set. Yeah. Then option C is there are 3 subgames in this game. Okay, so how do we count how many subgames are there in the game? So what do we mean by subgames? Like we try to reduce the game into some set of simultaneous games, and then we say that simultaneous game will be one subgame of that original game. And yeah, so reducing these to different simultaneous games will give us different subgames of the game. Yeah. So let's see how many subgames are there. So Actually, it can be seen that like again we go back to the algorithm which we talked about for finding out, let's say, the Nash equilibria. So here what like this is essentially what this algorithm is essentially doing is reducing the game into multiple sub games and then like playing those sub games and finding out the Nash equilibria. So here also we'll be doing something like this, that like we can see on this left side of the tree, like in this side, P3 and P2 have the same information. Like P3 also only knows that P1 has played L1, like nodes of P3, and nodes of P2 also only know that P1 has played L1. Like P3 does not distinguish between L2 and R2 here. So this means that there is one simultaneous game played between P2 and P3. Like all of this, like this P2, these two P3s, all of this can be reduced to a single simultaneous game. Like all of this can be reduced to a single simultaneous game, and like then you can find out Nash equilibria for the simultaneous game and stuff like that. So this is one simultaneous game. Similarly, this kind of thing will also be one simultaneous game because here also P2 and P3 have the same information. And then note that then like you can replace all of this subtree by a single Nash equilibria, and you can replace all of this subtree by a single Nash equilibria. And then what happens is the last game is just P1 deciding to play L1 or R1. So there are total like one sub game is the game of the left side of P2 and P3, the simultaneous game, and the second sub game is between P2 and P3 on the right side, and the third game is P1 deciding to play which game it wants to play, the left side simultaneous game or the right side simultaneous game. So that's why we have three games. So this is one game, this is two game, and like these are three. This is the third game. And note that like if one says, okay, why are you reducing three? Why can't you do it like four or five or something? Note that like there cannot be any more games. Like first of all, like these like yeah, like this will be one game, this will be one game, and like after P1 plays the game, you will have the final solution of the game. So like there are no more than three games. So yeah, correct. As one game is the simultaneous game between P2 and P3 on the left side. Second game is the, I'll just copy this. Second game is the simultaneous game between P2 and P3 on the right side. And third game is the game of P1 deciding whether to play the left side game or the right side. So that's why these are the three games. So that's why like there are three sub games in this game. Yeah, this is the answer. And like let's move on to option D then. So option D says that P3 knows that P2 has played, but it is not aware what P2 has played. So as can be seen in the options, like in this information set, also it can be seen that P3 knows that P2 has played because like P2 has played and that's why it has come to P3. But P3 cannot distinguish between L2 and R2. And here also P3 cannot distinguish between L2 and R2. So P2 can never distinguish between what P2 has played and what P2 has not played. So yeah, but it always knows that P2 has played something. So that's why this option is correct. As can be seen in the game. And then let's move on to option E. So every subgame starting from a node of P2 becomes a simultaneous move game. So every subgame starting from a node of P2. So this is like we have already discussed in option C also. So this is a subgame starting from one node of P2. This is a second subgame starting, and both of these games are actually simultaneous games. So this is correct option. So this is correct as discussed in Option C. Okay, so what options are correct? So A, C, D, E are correct. Hence, options A, C, D, E. I'll just underline this. So now maybe we can move on to the third question, which is again like asking pick the correct options for game one. So it's again like based on this game only. And what are the options? Options are like game one is nested, game one is ladder nested, game one is not nested, game one is not ladder nested. So let's just see. So we just have to check whether this game one is nested or ladder nested or what. So actually it can be seen that the game is indeed nested. And why is this the case? So the information partition for P2 is between these two subtrees, but note that for these two subtrees, there is no sharing of information by P3 across these two subtrees. So yeah. So I just directly check this using this information partition like between the subtrees, but you can also check whether like P3 what information does P3 have, what information does P2 have, and so on. So first of all, like we can ensure that we know that the game is nested. Now let's check whether it is ladder nested or not. So again, we can see that let's just check first for P2, the information sets for P2. So we know, so P2 no, so this information set of P2, this node knows that P1 has played L1. So the only additional information, so P1 does not know anything, but P2 knows that P1 has played L1. So the only additional information that P2 has over P1 is that is the action of P1. And note that this P1 is a singleton node. So till here it's okay. Like the difference information is just the action, and the action emanates from a singleton node. Similarly, here also P2 just knows something extra that P1 played R1, but this is a singleton node, so this is all right. Now let's check for P3. So this is the information set for P3. So these nodes for P3 know that P1 has played L1. But the same information only is known by like P2 also, that P2 has played L1. So here, like we discussed earlier, also like since this became a simultaneous game, that these nodes and this of P3 and this node of P2 share the same information. So and that's okay in ladder nested. The thing is, like if there is a difference in information, then it should only about the action. It should only be about the actions. But it is not necessarily that there should always be a difference in information. So it's okay. And here also, like there is no difference of information between P2 and P3. They have the same information. So again, it's okay. So actually the game is nested as well as ladder nested. So it can be seen that the game is nested as well as ladder nested. Hence, options A, comma B are correct. Right. Okay, then let's move on to the fourth question. So, fourth question is pick the correct options for the following game. So again, we have a game given to us. These are the information sets for the player 2, and these are the information sets for P3. And now we need to we need to find the correct options. So let's do it option by option. So like P3 knows that P1 and P2 have played. So in this game, does P3, so note that the information sets for P3, like P3 occurs after P1 and P2, right? So yeah, like this is kind of obvious that P3 indeed knows that P1 and P2 have played. So this option is correct. But it does not like, it's just asking about like, it does not ask about what have they played, but it just asks about what have they played. And as like nodes of P3 are like, the information sets of P3 are after information sets of P2 and P1, then this essentially means that it knows that they have played, as can be seen in the figure. or the game. Let's go to option B then. Option B says that P3 knows whether P1 has played R1. So, so note that these are the two information sets of P3. So this is one information set of P3, and this is the second information set of P3. And the option asks that does P3 know that? So the option says that P3 knows whether P1 has played R1. So note that P1 plays L1 on R1. So if P1 plays R1, then is P3 able to identify has P1 played R1 or not? But note that like actually P3 is not able to identify if P1 has played R1. Because why is it the case? Because uh, if P1 played R1 and P2 played R2, P3 is able to identify that because this information set is different from this. But if P1 played R1 and okay, like let me think about this option for a minute, guys. Like just a minute. So the option says that P3 knows whether P1 has played R1. So yeah. So actually this is incorrect because suppose P1 played R1 and P2 played L2. Then in that case, since these three nodes share the same information, so P3 cannot distinguish between P1 playing R1 or L1 because since these three nodes are in the same information set, uh, so these nodes can be reached by P1 playing L1 and then let's say L2 or something. So this information set can be reached by P1 playing L1 and then P2 playing something, or by P1 playing R1 and P2 playing L2. So P3 does not know if P1 has played R1 or not. P3 can just know whether P1 has played R1 and P2 has played R2. So like because this is in a different information set. So if P1 played R1 and P2 played R2, then P3 will know. But if just P1 plays R1, P3 will not know. Like if P1 plays R1 and then let's say P2 decides to play L2, then P3 won't know that P1 played R1 because then this same information set could have been reached from this side also. So this is actually incorrect as P3 only knows whether P1 played R1 and this and is important. Like this is a propositional and like if both of these events occur together that P1 played R1 and P2 played R2. So this is the event. This whole event in the parentheses, this is what P3 is able to tell. So like P3 is able to tell if these two things have occurred together, but it cannot identify these things on an individual level. Okay, so I hope this makes sense. So this statement is incorrect. And then let's move to option C. So option C says that P2 does not know whether P1 has played R1. So P2 does not know whether P1 has played R1. So actually this statement is correct because like both the nodes of P2 are in the same information set. So P2 cannot distinguish between L1 and R1. So actually this is correct. Like it does not know whether P1 has played R1 or L1. Correct. As both the nodes of P2 are in the same information. P2 corresponding to L1, R1 respectively and the same information set. And what does option D say? Option D says that the above game can be further decomposed. And what do we mean by further decomposition? Like, can the game be thought of as like some further simultaneous games or not? So let's see whether the game can be further decomposed. So for simultaneous games, like we have to check from the bottom and see like if any node has same set of information as the previous node. And if this is true, then one can actually say that the game can be further decomposed. But let's note here that mhm, like let's see if the game can be further decomposed. So let's see this information set of P3 and let's see like if this has any more information than this information set of P2 or not or something like that. So actually it can be seen that this information set of P3 so P2 does not know anything. It can be like one can easily see that P2 really does not know like anything, like because it cannot distinguish between L1 and R1. Like it just knows that P1 has played something, but that is not relevant here. But it can't distinguish between what P1 has played. Whereas P3 can distinguish between like P1 playing L1 and P2 playing R2. Like P1 playing R1 and P2 playing R2 with other things. Like P3 knows if this sequence of events has occurred, like P R1, R2 has occurred or not. So there is some information difference between P3 and P2. So it's not kind of a simultaneous game. It cannot be thought of as simultaneous game. And similarly, like this node also like has more information than this node. And since we have to like check for the last nodes first, so you can actually see like since P3 has more information than P2, uh, this game can really not be further decomposed into more games because yeah. And if one tries to see, okay, like let's just consider the game for P3, like since this information set, like these nodes of P3 have the same information, so can we divide the game, like can we think of the game as just uh, P3 playing something? So one game can be thought of as like just P3 playing something, but note that that also won't work. And why is this the case? Because like P3 won't know like from where has the like since these three nodes of P3 are in the same information set, so P3 really does not know like what node has occurred. So P3 really can't play a simultaneous game like saying, okay, I'll play L3 or R3 or something like that. Because it needs to know like from where has it occurred to it for it to decide on playing L3 or R3 or something. So correct. Uh, P3 has more information than P2. And hence they are simultaneous game. Or it's further P3 can't play the game of choosing L3 or R3 by itself. So like P3 can play this game obviously, but like this game really won't be like a decomposable game. Like it's not a game on its own of P3 deciding to play L3 or R3. And that's because yeah, because like P3 really like while deciding to play L3 or R3, in general, P3 will need to know the path, the previous path which has taken place for it to play the correct move. Note that in here, in this kind of a game, like you can see that the always playing R3 is better for P3. Okay, like let's just ignore these payoffs for now. Like, I think it's better to ignore these payoffs. Like otherwise they'll cause confusion because you really don't know like what for what player these payoffs are. Like, are these payoffs for player one, player two, or player three? Let's just ignore these payoffs. But yeah. So like for P3 to decide between L3 and R3, P3 really needs to know like at which node of P3 is it really present, because only then it can play like P3 or L3 or R3 like smartly. So this is not a game on its own of P3 deciding to play L3 or R3. As it needs to know the exact node from which it had to play. So yeah. So like P3 and P2's game is not like simultaneous game. Similarly, like P3's game in itself is also not like a sub game. So yeah. So this game cannot be decomposed actually. So options A, C, D are correct. It's options A, C, D are correct. Like this. I hope this makes sense. Now let's move on to the next question. So again, we have the fifth question, and this question also we have to find out the correct options for this game. Okay, now also in this game also, let's just remove the payoffs, because payoffs can cause a bit of confusion that for whose player are these payoffs actually, and it's not really relevant to us. So this is the game given to us, and then again we have to find answer some questions regarding the game. So the option A is at the left information set of P3, P3 knows that P1 has played R1 and P2 has played R2. So note that this is the left information set of P3. Like these are two information sets of P3, right? So at the left information set of P3, this set, P3 knows that P1 has played R1 and P2 has played R2. So in this information set, the option claims that the P3 knows that P1 has played R1 and P2 has played R2. So like R1 and R2 is like already on the right side, like it's not on the left side. So this is definitely incorrect. As can be seen. Okay, right. Let's move on to option B then. Okay, yeah. So she says that at the right information set of P3, at the right information set of P3, so for this information set, so P3 knows that P1 has played. So okay, P3 has known that P1 has played. It does not say what has P1 played, but P1 definitely has played because all the actions of P3 are after actions of P1 and P2. So it knows that P3 knows that P1 has played and also knows that P2 has played. So this is fine. And that P2 has not played R2. So this for this information set of P3, it claims that P3 knows that P1 has played and P2 has played. So that's fine. But it also claims that it also knows that P2 has not played R2. But note that in this information set, P3 really does not know if P2 has played R2 or not, because like these things are in the same information set. So here in this information set, P3 definitely knows that P1 has played R1, but it can't say anything about what P2 has played because all the actions corresponding to P2, L2, and R2 are in the same information set. So incorrect. As the nodes corresponding to L2 and R2, the right side, are in the same information set of P3. So yeah, so option B is also incorrect. Let's move on to option C then. So option C says that at the right information set of P3, so again about this information set, P3 knows that the sequence of strategies R1, R2 has not been played. So P3 knows that the sequence of strategies R1 and then R2 has not been played. Again, like this is also not known by P3 because P3 just knows that R1 has been played. It can't comment on anything by R2. So incorrect as had right information set of P3. Okay, maybe I should just correct. Same explanation as option B. Also, like maybe I should just add a note. The note is that P3 the right information set of P3 only knows whether P1 has played. So it can't comment on anything about what P2 has done, but it can definitely say that P1 has played R1, the right information set. Then option D is extensive form of the game captures the entire history of the game. So yeah, like this kind of thing, like this option is definitely like trivial because like extensive form of the game always captures the entire history of the game because extensive form of the game tells us like what one player played, what second player played, and like what actually happened. So yeah, so correct as extensive form of a game exactly tells us what the sequence of events that transpired in the game. So yeah. So only option D is correct, A, B, C are incorrect. So hence option D is correct. So yeah. Okay, I hope this makes sense to everyone. And yeah, now let's move on to the sixth question. Okay, maybe this is just a trivial question. So in an extensive form game, every player. Okay, maybe I should reword the question. In Nash in any Nash equilibrium of an extensive form game, every player is acting using backwards induction at every information set. So is this true or false? So the problem states that in any Nash equilibrium of an extensive form game, every player is acting using backward induction at every information set. So note that is this statement true or false? So this is like a very easy question. Like we have discussed this kind of question already. That this is actually false. Like so it says that in any Nash equilibrium, every player acts using backward induction. But note that what we had previously discussed was that there exists at one equilibrium where players are using backward induction at every information set and so on. But like there exists other equilibrium also, like there exists threat equilibrium or something where the players are not using actually backward induction. Suppose information sets were like singleton sets, like let's say the game was a perfect information game, then like every Nash equilibrium is not captured using the backward induction argument. Like there exists threat equilibrium also. False, as can be seen in by the maybe this has already been discussed, so I'll just keep the argument short. As can be seen by the existence of threat equilibrium in an perfect information game. Yeah. So threat equilibriums are also not that Nash equilibriums only. Like whenever you're talking about equilibrium, first condition is that it should be a Nash equilibrium, and then there are further relaxations or further restrictions on what do we call a threat equilibrium, what do we call the other type of equilibrium. So so yeah, so this is false, and this is like not too hard to see. Then maybe we can move on to the final question of the day, which is the seventh question. In the seventh question, says that consider the following zero-sum game and write the game in its normal form. What is the size of the normal form matrix? P1 is maximizing and P2 is minimizing. Write the size as number of pure strategies of P1 times number of pure strategies of P2. So essentially, the problem is asking us to write this game. So this is an extensive form of the game. And note that this is a multi-act game because P1 is acting here. You can see that P1 is acting twice, whereas P2 is acting only once. So it's a multi-act game. And the problem asks us to write this game in its normal form. So this is the game given to us, and we want to write the normal form of this game. So yeah, so this is note that this is a bit of a tricky question and an interesting one at that. And like if this was just like let's say a player P3, this was player P2, and this was player P1, then it would not be so difficult because then for single act games we previously also discussed how to write normal forms in the last session also we had a problem like this. But in multi-act games, it really becomes somewhat more interesting as to what's going to happen. Like P1 is playing twice, so you need to be a bit careful while constructing the strategy space for P1. Okay, so maybe let's just see what are the possible strategies for P1. So note that again, like strategies will be functions, strategies which will be functions. So we already discussed this, right? That a strategy in a normal like a strategy for a player in an extensive form is just a function of what other players are going to play and something like that, right? So like what are the possible functions? Let's just do it. Maybe I'll do it by numbering. Yeah. So what's the first possible strategy for P1? So so player one is playing twice. So first possible strategy is maybe uh, like let's say okay, maybe I'll just write it like this. So so there are like P1. So the possible strategy for P1 will be like so P1 acts at multiple stages. So strategies will look like this: that P1 plays something at stage one, and P1 plays something at like P1 plays something in first turn, and P1 plays something in the second turn. So it will be a composition of like two strategies. And this is what makes the writing of like what P1 actually is going to do a bit more difficult. So let's see here. So uh, first possible strategy will be, so note that right now in the first possible space, like P1 knows nothing. So it can just play L1 or R1. So P1 plays L1 uh, in, okay, maybe I should just write this. P1 plays L1 in first try. So maybe like first chance because P1 has two turns. So maybe I should like turn in first turn and then so and in after that if P1 has played L1, then what's going to happen is the game is going to be restricted in this kind of a space, right? And note that now P2 can play actually L2 or R2. But note that whatever P2 plays, like P2 can play L2 or R2, but these two nodes of P1 are in the same information set. So P1 does not know whether P2 has played L2 or R2. So this will not be a param. So P2 playing L2 or R2 will not be a parameter for P1 at all because both of these nodes of P1 are in the same information set. So P1 really cannot distinguish between what P2 has played if P1 has played L1. So what this means is that the only thing which P1 can do again is like some kind of a constant function, which is just playing L3 or R3. So P1 plays L1 in first turn. Okay. And plays L3 in second turn. This is first possible function, and in second possible function, it will play R3. Right. So, like, these are the only two possible strategies for P1 if it has played like L1. And why is the case? Because like now P1 cannot see what P2 has played. And since it cannot see what P2 has played, like it won't like P2 playing something will not come in as a like parameter for the function or the strategy. So it just plays now again as a constant strategy of L3 or R3. But if P1 plays actually R1, the third strategy will be P1 plays R1. Then it can actually distinguish between like P2 playing L2 or R2 because these are in the same different information sets. So now if P1 plays R1, then P1 knows like uh, like what P2 has played. So if P2 plays L2, then then P1 has like two strategies like playing L3 or R3. So then P1 plays, let's say L3. So so P1 plays R1 in first turn, and P2 plays L2, and P1 plays L3. Um, maybe it's not good to write like this. So like if P1 has played L1 R1, then actually like the in the second turn, like essentially the strategy for P1 will be kind of a function. So we should really write this like a function. Like, and yeah, so maybe writing like a function should be like this. And plays L3 in second turn. If P2 plays L2. So this is the first parameter for the function that okay, P1 has played R1, that's fine by us. But after that, uh, P2 can play actually L2 or R2, right? So this is a parameter now. So the function will be like, so the second strategy for P1 will be a function of P2 playing L2 or R2. So if P2 plays L2, like, so the first possible function will be playing L3 in second turn if P2 plays L2, and like, and if P2 plays R2, then like it will be a parameter of what actually P2 is playing. So P2 is playing like whether L2 or R2. So if P2 plays L2, then P1 plays L3, and if P2 plays R2, then also it plays L3. So let's say this is the first function, and now the second function will be like so P1 playing L3 in second turn if P2 plays L2, and playing R3 if P2 plays R2. Like we have fixed like P2, like so it will be a parameter of P2 playing L2 and R2. So these things will be fixed. And now these things will be varying actually, like what does P1 play in its second turn. So first turn is fixed that P1 is playing R1, but second turn will have a parameter of what P2 is playing. So L3, 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 R3, and then we have maybe R3, L3, and then R3, comma R3. So we'll have something like this that yeah. So this so is this correct? Let me just think about it for a minute, guys. So the first possible function is P1 playing L1, but if P1 plays L1, then it does not know what P2 plays. So then P1's actions will just consist of a constant function that it will just say whether it wants to play L3 or R3. Right? Then P2 can play some things, R2, and if P2 plays H2, then my strategy will be yeah. If I don't know what the other person is going to play, then I have to play a constant strategy. Yes, I think this kind of makes sense. Yeah, that if you're doing it L, if P1 goes into L1, then it knows that it does not know what P2 is going to do. And so like it can, and it cannot even see what P2 has done. So it will just enter that. It will go by L3 or R3. But if P1 plays like R1, then P1 can see what P2 has played. So P1 strategy will now expand to seeing first like what P2 has played. So if P2 plays something, if P2 plays something, so this will be a function. And like for these possible values, like there will be like, there are two choices of L3 or R3 for P1 in like, and so there will be these four scenarios, right? So I hope this kind of makes sense. These will be the possible strategies for P1. And I don't think there will be any other strategies for P1 because it can play first L1 or it can play R1. So yeah. So and we are just talking about like pure strategies. So deterministic strategies, not randomized. Otherwise, randomized will be like infinite in number. And for let's see what will be the possible strategies for P2. So for P2, it's easy. So for P2, note that uh, P2 cannot see whether P1 has played L1 or R1 because P2 is in the same information set. So uh, so the first strategy will just be playing L2 or second will be R2. Are just playing L2 or R2 because P2 really does not know what P1 has played, so it will just have a constant strategy of playing L2 or R2. So yeah, hence there are 6 strategies for P1 and 2 possible strategies for P2. So, so note that like this was a bit interesting and it was like, so the interesting case was when like P1, like for finding out the strategies for P1, and this was interesting as well as like very like non-intuitive, or let's say like it was a like it required a bit like technicality in this. Like we had to see like if P1 plays certain strategy, then can it see what happens to P2 or can it not see what happens to P2 and something like that. So if these were, let's say, perfect information, if the game was a perfect information that these nodes were like perfect informations, then actually it would have been much easier because then one possible strategy for P1 would be for like P1 can take either L1 or R1 at the first stage. If P1 takes L1 and then it can see what P2 has played. So there will be like two possible choices for what P2 has played, and for both the possible choices, there will be like two possible choices for what P1 wants to play. So there will be like four possible choices for what P1 wants to P1 can like four possible choices for the functions if P1 has played L1. And then similarly four possible choices if P1 plays R1. and then the number of possible strategies will be somewhat equal to 16 or something. 4 into 4. I think it will be something like that. Like if the game was a perfect information, but since the game is not a perfect information, then like, these kinds of weird things happen. That like if you play something at the first stage, like if you play something, then you might not be able to identify what the other player plays at the second turn, and then you have to play something constant. And similarly, if you play something else, then you might be able to identify what's happened, and then you will be able to here you will be able to distinguish, and then you'll have more functions. So yeah, a pretty interesting question. And yeah, this is the final answer for us, that there are 6 possible strategies for P1 and 2 possible strategies for P2. And yeah, just mentioning that these are pure strategies. We are not talking about randomized strategies. And maybe size of the normal matrix will be something like 6 cross 2, because 6 strategies for first player, 2 strategies for second player, and yeah, one can write the game in its normal form also. Like so, just you just need 6 rows and 2 columns, and just see like what each of these things result in the yeah, like I don't think I need to uh, explicitly write out the normal forms, because it can be done like by yourself also. Like just like first row will correspond to like this kind of function, second row with this function till 6 rows, and then 2 columns will correspond to like P2 just playing L2 or R2. And then you can see like what kind of thing happens here. So okay, then I think this was all I had to discuss for today, and yeah, we are almost out of time also. So yeah, I think in today's session we focus a lot more on theory, because like this week's lectures were a lot more theoretical in nature, and like they dealt with a lot of like definitions and something, but we tried to get a brief overview of those definitions and what do they intuitively mean, and then we discussed some problems related to them, and in the end did a like very interesting problem. I think this was the main problem which I wanted to discuss for the day. Others were somewhat easier. Right. Okay, so I guess this is it for the day, since there is no one present in the no one is actually like present in the meeting itself. So like there are no doubts, and yeah. So thanks for watching the session on YouTube, guys. Hopefully I'll see you guys in person next week, Monday 6 to 8 p.m. So till then, I'll just stop sharing and goodbye. Meet you next week.